So, for the records, welcome everybody again. Today we have our first pizza seminar of the season, and we are very happy to have Lavinia Paiella from the Gran Sasso Science Institute in L'Aquila, close to Rome, Italy. And she will talk about something related to her PhD project about how we form black holes. So, please, the floor is yours. And
Okay.
I'll tell you when you have 5 minutes left.
All right. Okay, so good evening, everyone. As we were saying, I'm Lavinia, and I'm a second year PhD student at JSSI. So today, so we talked to you about a bit of how to grow heavy black holes in star clusters. And this is a project that I've been working on since a year or so. My supervisor, Manuel Casetta, and Goroganesian, and as Davide was saying, please move. Nope. Well, let's make
By the other way?
it. Well,
It froze.
let's see.
Let's click on presentation.
Yeah,
Okay.
let's see. Okay. All right. So, okay, so this is me, and my main research interests are intermediate mass black holes, population studies, and multi-messenger astrophysics. But indeed, I'm studying in JSSI, which is a very, this is a bit of an advertisement, I must say. It's a very diverse environment, so there's many people working on different fields. Among those, also Stefan was here and invited me. Thanks, Stefan. And nothing. So it's most projects are very intersectional, and this is very good. But as I was saying today, I will talk to you more about these two things. So intermediate mass black holes and populations of black holes in star clusters. So, okay, so this is going to be a bit basic, hopefully very clear. So you can imagine that there are two different astrophysical categories of black holes, at least. And those are stellar mass black holes. Well, this is not good. Okay, let's hope it works.
Go ahead.
Anyway, so you have stellar mass black holes, which come from the collapse of massive stars, and they can reach up to roughly 100 solar masses. And on the very other side of the mass spectrum, you have supermassive black holes, which are heavier than 10 to the 5, 10 to the 6 solar masses. And these have much more complicated formation pathways. And those are the black holes that basically we observe at the center, the center of galaxies. Now, one big open question is, again, relating the formation of these very massive beasts, is whether, for example, a stellar mass black hole can actually grow up to supermassive scale. So by which processes and if it is possible. And one way of tackling the problem is adding a new ingredient to the mix, which are intermediate mass black holes, which, as the word suggests, are in between these two categories and fill the gap in 100 and roughly 10 to the 5 solar masses. And as you can imagine, these black holes are very interesting because they may reveal something about the connection between these two categories and whether this connection exists. By themselves are really interesting also because, again, like they may be seed for the formation of supermassive black holes. So basically the building blocks from which you want to start to build a supermassive black hole. Now, of course, as you can imagine, this is not so, it's not so easy to say something about these objects because, let's say, among these three categories, this is the most underrepresented category of black holes. And there are many different scenarios that are explored for these kind of black holes, but we still are not sure which is the most favorable scenario, let's say, to produce these black holes. Now, one scenario that I'm studying is the formation of intermediate mass black holes in star clusters. Star clusters are basically gravitationally bound systems of stars, and you can imagine that these are good environments for the formation of an intermediate mass black holes because they are dense environments, which means that the objects in the clusters have the chance of pairing up, colliding, merging, and so building heavier and heavier objects under, of course, specific conditions. Now, a star cluster, let's say if you want to really simplify the picture, you must imagine that a star cluster is mainly made of its core, which is the central region of the cluster. It's the densest region, let's say, and then the surroundings. And the most fundamental properties of the cluster, as you can imagine, are the mass of the cluster, the radius of the cluster, which, however, is usually, the radius used is the half mass radius, which is the radius that contains half of the mass of the cluster and depends on the density profile you choose for your cluster. And among these other parameters, you also have the escape velocity. So the escape velocity is, if you want, kind of sets the boundary of your cluster in the sense that any object that it's moving at the speed that is faster than that, it's going to be unbound with respect to the cluster. And this escape velocity goes as the square root of the mass of the cluster and the radius of the cluster. And this means that for very massive and very compact clusters, you have a high escape velocity, and so you have a higher chance of retaining the objects within the cluster. And we'll see this is going to be useful later. One last thing is that the core also is a very important, let's say, section of the clusters, as we shall see. And it is usually inhabited by the most massive objects in the cluster, such as black holes, because indeed those black holes basically migrate towards the center because of processes such as dynamical friction within the cluster and also energy equipartition within the cluster. So, okay, so this sets the picture, let's say. Now, let's add a layer of complexity. Star clusters are not static. They evolve through time, and there may be a best time, let's say, to produce an IMBH. Star clusters, let's say the evolution of a star cluster, so the evolution of its mass and radius, usually scales with relaxation time, with the relaxation time being, say, the most fundamental time scale described in the cluster, and it is the time it takes for a star to lose memory of its initial state, especially if its initial velocity, because of repeated interactions with other stars in the clusters. It can be, it was proven that there is another time scale, which is a fraction of this relaxation time, and it's very fundamental for the cluster, which is the core collapse time. And as the word suggests, the core collapse time is really the time on which the core of the cluster, so its densest region, collapses and becomes even denser and denser. And you can imagine that this is a good time to produce heavy objects because, of course, the core is getting denser. And so all the objects within the core are having even a higher chance of interacting with each other and merging. Now, fixing a core collapse time means that you are looking at specific ranges in mass and how fast radius of the clusters. And indeed, as you can see from the plot, here I drew different lines of equal core collapse time, and you see that the time is decreasing in this direction up to some point where it reaches 5 million years. So for clusters which have a core collapse time like that, like super short, because like million years is again like the lifetime of a massive star in the cluster, weird things can happen. And specifically, what can happen is that you can go through runaway stellar collisions within the core. So basically, as I told you before, the core is inhabited by the most massive objects in the cluster. Now, if the core is collapsing on a time scale which is shorter than the typical time scale on which stars produce black holes, that means that the core at the moment of core collapse is inhabited by massive stars. And it was proven in this, by Portuguese work and Macmillan in 2002 that there's actually that actually these stars can undergo runaway stellar collisions, meaning that a massive star collides with another massive star, and that it's a repeated process, which is also accelerating because at each interaction the star becomes bigger and heavier, and so its cross section it's larger, and so it has an even higher chance of meeting another star and growing up more. All right, so okay, so take a message for clusters with core collapse time less than 5 million years. You can go through runaway stellar collisions. You can produce very heavy stars because, of course, you undergo these many collisions and you build up very heavy objects. And the mass of the very massive star is roughly proportional to the initial mass of the cluster. And once this very massive star dies, you can produce an intermediate mass black hole in the center of the cluster. So this is a very fast way of producing IMBH within a cluster. Now, if you're not in this case, you still have a chance of producing an intermediate mass black hole, but you have to rely on black holes. So your massive stars have died, you have all these black holes, and these black holes still have a chance of being binaries, merging, meeting other black holes, and basically going through repeated chains of black hole mergers. And this scenario is also called, for the formation of IMBH, it is called hierarchical black hole merger scenario because indeed you go through repeated mergers of tiny black holes. Now, the problem with this scenario is that it's not so easy to actually repeat many mergers all over again because there are some conditions for which your black hole or your binary may be kicked out of the cluster at some point. And these conditions are basically either your binary can gain some kinetic energy by close encounters with other tiny black holes in the cluster and gets recoiled out of the cluster, and so it merges out, of the cluster. Otherwise, the binary merges within the cluster, produces a black hole, but the fact is that the black hole at birth has a relativistic kick. And if the kick is, again, larger than the escape velocity of the cluster, you have no chance of meeting other black holes and growing more. And if you recall, the escape velocity is proportional to the mass of to the square root of the mass of the cluster. So more massive clusters, more massive and compact clusters have a higher chance of retaining their black holes and producing black holes, heavy black holes through this scenario. All right, so key points. Again, IMBHs may serve as seeds for the formation of even heavier black holes and be the connection between these two categories of stellar mass black holes and supermassive black holes. You can produce them either in star clusters, either by runaway stellar collisions or hierarchical mergers. If you go through the first scenario, you must have a cluster with a core collapse time of roughly less than 5 million years, meaning that you are looking at this region here in the mass and radius diagram. If you go through the second case, your cluster needs to have, intuitively speaking, a large escape velocity, which means that you must find yourself up here. And we're going to see that with simulations. Okay, so going through my work, I'm going to show you the results of a simulation of 4 million black holes, this simulation was done using BPOP, which is a code written in C++ by my supervisor mainly, and it is not still public, but we're working on making it public, and it's a semi-analytic code, meaning that it relies on some analytical prescription to actually model the dynamics of the black holes in the clusters. And let's say the gain is that it's very fast. And my simulations, as I was saying, is of 4 million black holes. Half of them are in globular clusters and half of them are in nuclear clusters. Now, for the purpose of this talk, there's no, let's say, actual need for now to actually go into the details of the differences between these two families of clusters. But what you have to keep in mind is that, again, they span different ranges in mass and radii in the mass diagram. So you can expect them to contribute differently to the two formation scenarios that I was talking to you about. And okay, so that's it. All right, let's go into some results. So just need to introduce you something more and then we're done. So the first part of my work was to actually look at the final fate of an IMBH. meaning that once it is formed, an IMBH can either be, again, ejected out of the cluster, or it can be retained in the cluster. So at the end of its growth, it may be found out or in the cluster, depending on what processes it goes through. Just nomenclature-wise, expelled means out and retained means in. And an IMBH can be either expelled or ejected if, as I was saying, the binary gets basically a close encounter with a perturber, which gives off some kinetic energy, and the binary is expelled out of the cluster. Or what can happen is that it's recoiled in the sense that the black hole is formed by a black hole merger, but its relativistic kick is so high that the black hole is thrown away. Otherwise, it can be retained in the cluster, and it can be retained either as an inside black hole, which means that basically the black hole has finished all of the other black holes, so it cannot grow further just because there are no more tiny black holes to grow from. Or it can be an Highlander black hole, meaning that basically the next merger would happen at the and would exceed the time of the simulation, which is basically the age of the universe. Okay, so the first question we wanted to kind of answer were how is this final fate of an IMBH linked to the seeding scenario, and how is it linked to the properties of the cluster? And so here you can see some plots. So the top row refers to IMBHs formed through runaway collisions, and the second plot refers to hierarchical mergers. So as you can see, the different colors refer to the different fates that I was introducing to you. And you can see that there is a strong dependence, of course, of the final fate of an IMBH with both the mass and the density of the cluster. Density basically encoding the information also on the radius. And what you can see is that the more massive or the more dense the environment, as I was saying, the better it is for the IMBHs to be retained. Because as you can see, for example, the inside fraction here, which is on the y-axis, sorry, I didn't say this, but on the y-axis, there is the fraction of IMBHs ending up their life as they're ejected, recoiled, and so on. And you can see that the fraction increases as you of retained black holes as you increase the mass of the cluster or the density. And this is again to be expected for the reason I was saying, so that the massive clusters have larger escape velocities, and so it's easier for them to retain their black holes. But you can see also there's a big difference if you consider black holes which are IMBHs which are formed through hierarchical mergers or runaway collisions. Indeed, while on the first, on the top row, you can see that there is kind of a transition, no? Around 10 to the 5 solar masses, you see that the line corresponding to the inside black hole goes up and basically crosses the one of the recoiled. So the fraction is of inside black hole is becoming more than the one of the recoiled. So you have a higher chance of retaining the black hole rather than getting it expelled. This doesn't happen here for a hierarchical merger. You actually never reach the point to which these two lines cross. And this is due to the fact that an IMBH formed through runaway stellar collisions, it's actually very heavy at birth. And being very heavy at birth means that when you merge with another black hole, the chances of you getting a high relativistic high relativistic kick is actually low, because the relativistic kick is as larger as more similar are the black holes that merge. So since IMBH is coming from runaway collisions are much heavier than all the other black holes, they are actually not receiving so large kicks, and so they are basically retained in the cluster easier than those that undergo repeated mergers with other tiny black holes. Because of course, if you grow an IMBH through this scenario, that means that at least for the first mergers, you are meeting black holes which are very similar to you. And so you receive very large kicks. All right, so next plot. So these relates more on the formation time of an IMBH depending on its mass. So here we wanted to see how much does it take for an IMBH to form, given that it is seeded through runaway stellar collisions or it is formed through hierarchical mergers. And indeed, you can see on the x-axis there is the mass of the cluster. On the y-axis, there is the delay time, which is the time it takes to actually produce such a massive black hole. And this line corresponds to runaway stellar collision seeds, while this upper line to hierarchical mergers. And so this is a bit more maybe complicated to see, but what you can see here is overall runaway stellar collisions are able to produce black holes of up to a few 10⁴ stellar masses, always on times which are shorter than the hierarchical scenario. And this is, of course, due to the fact that, again, like you're seeing a very heavy black hole early in the evolution of the cluster. You can also see that you kind of have these, so you don't go much further than 10⁴ stellar masses. And this is due to the fact that, as you may recall, I can show you also, as you may recall from here, actually, if you want the core collapse time to be less than 5 million years, that means that you are fixing the maximum mass of the cluster roughly at 10⁶ solar masses for reasonable clusters. And that means that you are basically fixing the maximum amount of massive stars you have in the cluster. So you have a fixed amount of stars, and you also need to imagine that a lot of them are going to finish in the formation of that IMBH. So once the, sorry, my throat is killing me. So once the IMBH is formed, there are not many more black hole progenitors around. And so you actually are depleting the environment of possible stellar mass black holes. And so you cannot grow much more than you are actually being seeded. Because again, because on the limit on the mass and on the depletion of massive stars. So that actually basically cuts your maximum mass of an IMBH through this scenario around a few 10⁴ solar masses. For the hierarchical scenario, you see that you take more to build these black holes, because of course you have to start with very tiny black holes and you have to go through a lot of mergers, but you can grow very heavy, of course, given the fact that we are actually simulating also extremely heavy nuclear clusters like 10⁹ solar masses. So these, let's say, upper tail here, it's a bit pushed to the limit, but again, if the cluster is very massive, you can actually reach even 10⁶ solar masses. Okay, so this other plot goes a step further. So we have heavy black holes forming. When do they form? So what redshift do we see them, and what happens in time to the mass spectrum of black holes? And so every snapshot here is a different redshift. Again, like caveats, we are pushing a bit our hypothesis because we are assuming that we have very massive clusters even at redshift 7 or 8, which is a bit to the limit, but we kind of wanted to see what happens. I mean, at what redshift we would actually find those heavy black holes in this case. And you can see that even at redshift 6 or 7, your mass spectrum is already showing black holes of roughly 10⁴, 10⁵ solar masses. And of course, the more you go in time, so the more you wait and the more you populate these beams, because the more time you have for these black holes to actually grow. Sorry, here I'm looking at the dashed line, which is the one referring to the hierarchical formation scenario. So I was looking at those very massive black holes that we find. Again, though, this depends on very much on the clusters and on the formation history of the cluster. So if you allow massive clusters to exist at high redshift, with which masses and so on. So it may change drastically if you change the formation history of the clusters. Okay, so final plots. So this is called Sakura plot. Honestly, it's not my idea. Like my supervisor saw it and he was like, "Oh, Sakura seems like a Sakura tree." So let's set it like this. So this is a Sakura plot. And this is similar to the one that I showed you before. So here we are looking at different snapshots in redshift, but now we want to see where the IMBHs are forming. So you have again the mass, the radius, the color is the mass of the IMBH, the orange ones are the heaviest ones, and of course, as you expect, the more you move in time, the more orange you get. But where do you get it? You get it for the most massive clusters in our sample. So for the nuclear clusters that have roughly masses above 10 to the 7 solar masses. And I think, again, here are the ejected ones. The IMBHs that form are ejected immediately, and these mostly forming globular clusters. And one thing that is interesting is, but we have to investigate it more, is, so here's a zoom in of the first 3 snapshots. You see that seems like the distribution of IMBHs moves in this direction, and it gets cut at different collapse times. You see that here, for example, it's cut around 100 million years, while here it's cut around 1 giga-year. And we think that this may be a hint of the fact that, again, the core collapse time is really the time on which IMBHs are formed, or at least the time on which an IMBH is formed in a massive clusters may be a fraction of the core collapse time, and we are wondering whether there is actually a fixed fraction, let's say, like whether there is a common fraction of the core collapse time on which these IMBHs form for different clusters. But this is, let's say, open question. Okay, this is a nice GIF, and with this is my last plot, if I am not mistaken. So here again, mass and radius of the cluster. You see the distribution of runaway stellar collision seeds in red and the hierarchical mergers in light blue. And again, like an open question here is, what are the edges, again, of these distributions? For runaway stellar collision seeds, it's quite trivial because as you see, you have like horizontal cuts whenever you look at IMBHs of increasing mass. And this is kind of reasonable because the mass of the black hole is kind of proportional to the mass of the cluster, because mass of the black hole comes from the mass of the very massive star, which is proportional to the mass of the cluster. So if you want to see heavier objects, you have to look at heavier clusters. For a hierarchical merger, this is really not trivial. And honestly, I'm not sure which are the edges of these distributions. For example, one could say, okay, maybe I draw a line at density, and the density kind of seems to cut my distribution. But again, this is something that I want to investigate a bit further. And if you have ideas, please please tell me. But I think it's really interesting because it kind of seems, it goes in the direction of like relating the mass of an IMBH to the properties of the environment. Okay, so conclusions. We have, I hope I didn't run, but anyway, so we have simulated 4 million black holes, both in globular and nuclear clusters, and we wanted to assess the combined role of runaway stellar collisions and hierarchical black hole mergers. We saw that the final fate of an IMBH is very, very much linked to the mass and density of a cluster, and especially we see that more massive clusters are better at retaining their black holes, which is expected, but also that, and here I didn't mention it maybe, but also that runaway stellar collision seeds are better at being retained because of their heavy birth mass. Clusters in which runaway stellar collisions happen, they can grow very fast IMBHs, but they cannot go much further than a few 10 to the 4 solar masses, which would be said. But it's intrinsically, I mean, it depends on the fact that the mass of the cluster is not so, it's fixed by the core collapse time limit, and you have depletion of massive stars. And we see that there are interesting heavy black holes that we can form, but these are formed in the very heavy nuclear clusters that we are simulating. And so we now want to see more about can these clusters form at a redshift? Like maybe we can of course, push the limit a bit lower and see whether we can form them at some epoch in time. these very heavy IMBHs. And one other thing that I would really love to, get to know more, and is whether one can relate the population, let's say the IMBH black hole mergers happening in a cluster, to the properties of the cluster through gravitational waves, meaning that I see this, I don't know, 10 to the 3, 30 solar mass event. Can I say something about which environment it has to form? It has to be this massive, this compact, and so on. Okay, so with this, I thank you, and I put the slice of pizza. Just very fast.
Thank you, Lavinia. So we have time for questions.
Very nice question. What will be the difference in simulations or in case of your cluster of 4 million black holes and 4 million of mechanical particles in vacuum?
You mean time?
Quality different. Because you surely consider black holes as particles, let's say, of specific mass.
Yeah, indeed, yes. I'm not sure. I mean, it's the problem is that they are like, if you consider two black holes in isolation, then there's not much physics you have to take into account, in the sense that you just need to integrate Peter's equation and just see what is the time it takes for them to merge. Of course, like here it gets more complicated, because in the meantime that the binary is living, you have to compute the time it takes, like for example, the time it takes for it to be hardened. So basically the binary shrinks because of interactions.
So time is different.
Sorry?
So time is different.
I mean, the physics completely different. Like, it means if you put a binary in a star cluster, you have to account for completely different things. Again, as I was saying, like dynamical interactions with perturbers, and so yeah. I mean, but it's much easier, let's say, to to simulate just the isolated one, I would say. But I don't know if, sorry, I don't know in which direction you kind of wanted your question to. Okay.
I have a question about the runaway scenario, because just a clarification. When in the runaway scenario, you have this massive star that merge, right?
Yeah.
And then the black hole is formed, the intermediate mass black hole is formed by this supermassive star.
Yeah, I mean,
but then how can you reach thousands of solar masses? Because I thought that at around 1,000 solar masses, then you reach the Eddington limit, and the upper layers are thrown out for massive stars. But I might be wrong. But
no, I mean,
discussion about this ages ago.
There's actually, I mean, there's a big discussion on whether you can actually form these stars, in the sense that the physics of how these very heavy stars can actually regulate themselves and be stable is really, I think, kind of not known so much. The very simplistic assumptions that you make to avoid, let's say, layers of the star being thrown away, is that you limit yourself to very low metallicities. And that kind of saves you from, for example, pushing the layers of the stars out, because you are kind of like reducing wind losses. But again, like this is
For the wind, yes, but I'm talking about the you reach Eddington limits at some point. So you basically throw out the hydrogen envelope anyway. And so it's not just a wind magnet.
Yeah.
But I don't know. I remember there was a discussion because I was following this field 15 years ago. I have no idea, so I could learn after this. But I remember there was a discussion that 1,000 was more or less the limit. But because I saw that you discussed 10,000 or so.
Yeah.
So you need a ginormous star to do that.
Yes.
I was just wondering how.
I'm not quite sure. I'm not quite sure, to be honest. I didn't look into that. Thank you for the comment.
So I was interested in the last working how you can use gravitationals. So can you expand on this a little bit more? So first of all, also how so we can measure things like over eccentricity or misalignment of the spins, if you've heard.
Mhm.
How how that helps you, or what kind of information would be most useful for you to measure, or what you're thinking of how
So, I mean,
how
the
can we
sorry.
nail down information about that.
So honestly, my very naive idea for now was to, I mean, looking at this plot, I was like having this idea in a sense that, as you can see, I mean, the more you increase the mass of the IMBH, the more you're kind of selecting specific regions in the mass and radius diagram. So even just like measuring if you are able to measure a gravitational wave event with an IMBH and a stellar mass black hole, and the IMBH has a specific mass, maybe like thousands of solar masses or more, then that actually tells you that these IMBH cannot form, let's say, I mean, at least not in isolated binaries where nothing has happened, like probably maybe it can grow through accretion, but I mean, I would say it's a bit difficult to find such a heavy binary out of star clusters. Well, no, I mean, there are other scenarios, but let's say if you focus on star clusters, you say, okay, in the hypothesis on which these binaries formed within a star cluster, having that these IMBH is this massive, what would that say about the mass and the radius of the cluster? And in this plot, you see that the more you grow in mass, the more you're kind of selecting this portion of the parameter space. So let's say, my idea was to kind of see whether you can actually relate such an event to a portion of this parameter space. Of course, as you've been saying, also like spins can help because dynamical, especially if the binary is formed dynamically, you don't expect the spins to be aligned. So if you see very misaligned spins, that might actually be a hint also of a dynamical merger. So, but yeah, this is still the same very tiny idea for now, but we'll see. I will let you know.
But the problem is that something like that, what really hit. So 1,000 solar masses, that's at the edge of what you can measure.
Yeah.
And then you can only see a very short signal, and it's really hard.
No, indeed, yeah.
But-
Yeah, with my supervisor, we're discussing more like to use this as a kind of let's say case scenario to propose like milliards or so interferometers, like as a case study for other kinds of interferometers.
I think there was another question over there. Well,
Intermediate mass black hole can be also found in Lavinia galaxies. So at higher redshift, this stellar, this various stellar cluster can be like the seed of dwarf galaxies.
I don't know. I mean, sorry. I mean, I'm very let's say this is the direction I want to go, but I really need to study this in more details. But yes, in principle, you can kind of relate this also to galaxy formation. Like you see this very heavy black hole, and you say, oh, okay, this may have formed in a dwarf galaxy at redshift. So, but I don't know. Sorry, I need to check it out.
In the simulations, especially in the case of people mergers, and how important is the simplicity?
I think it's mostly. Let me think. I would say not so much. It's mostly important in the merger time, let's say, to actually decrease the merger time, but
The time by then they met is important, or it has already been.
no, it is. I was just like wondering whether it's important on the dynamical time scales. The fact is that the merger time is the last one you reach, basically. I mean, once you go through all that exit, let's say, conditions. So it's important, of course, like to kind of like regulate the time of merger of the binaries. But dynamically speaking, the time scale on which, I don't know, like the black hole goes to the center of the cluster, meets another black hole, and the binary gets hardened, it's not so relevant in these other like timescales.
Bless you. So first of all, thanks a lot because it was very nice and clear talk for us. I mean, it's a lot of work. So yeah, probably naive question, sorry. Because you run simulation for both global and nuclear clusters.
Yes.
And I think you said that in global cluster it's harder to retain the intermediate mass black hole. So it means that we should not expect to have any intermediate mass black holes in our global clusters, in our galaxy at all, or that can be. Like we have a fraction of global clusters that
I don't know a fraction. No, so so it is usually more difficult both because they are less massive and so again like they have, let's say, smaller escape velocity compared to nuclear clusters. Plus nuclear clusters are usually more densely peaked at the center, so it's even better, let's say, at retaining other black holes. I don't have the plot. I had a plot actually comparing so let me say make you imagine this plot. But I had a plot with the mass of the cluster and the mass of the IMBH. And if you kind of compare the IMBH in our simulations to the ones to the masses of clusters in the Milky Way, you see there is a superposition between the IMBHs we found in our simulations, but they mostly come from the runaway seeding scenario, in the sense that it's very unlikely that they can actually go through the formation through hierarchical mergers, because as you were pointing out, the escape velocity is smaller, so the chances are that the black hole gets expelled right after the first few mergers. But if the globular clusters is sitting in this kind of region, also like this is initial radius and initial mass, so you also need to you'd say assume a prescription for the evolution of these two quantities, which is really non-trivial. But at least if it has like the right masses, you can expect it to have an IMBH which may be formed at the beginning of the evolution of the cluster through runaway stellar collisions. So there was quite a bit of a match with the globular clusters in the Milky Way, but just for the black holes which were simulated in a runaway stellar collision scenario.
Kelly, one last question.
There are also these young dense stellar clusters in the galaxy, like
Yeah.
one. Is that something where the runaway scenario can apply? I mean, they are not as massive. It's like
Yeah. I think so, yes. I mean, wait, let me check the other slide. I don't remember. Sorry, yeah. Oops. No, this here I didn't. I have to say that I am. Whoop. No, what am I doing? I don't remember the radii of these, in the sense that they are indeed light enough to fall in this region here, not 10 to the 5, and so on. Less. I don't remember if they are also found to be this compact, but I think yes. I mean, they're also good candidates for this kind of scenarios. Again, like this is a bit of an extreme scenario in the sense that it's a runaway process. So maybe in reality you may have, let's say, not really a runaway process, but still you go through multiple collisions between stars, and I would say, yeah, it's reasonable. Yes.
It was a fun question. Because if I well understood, you have two situations where either you have 100% black holes or 100% stars, which merge to form these black holes, right? The runaway and the energy.
Yes, I mean, not.
Yeah.
Sorry, go ahead.
No, because yeah, the question was, would it make sense to consider a mixture of these two? Why do you consider them like parallel?
No, okay, so let's say very good clarification is that the stars that you don't find at times higher than 5 million years are the most massive stars. So actually, it's not that the cluster is like only made of black holes. You also have tiny stars, like less massive than 150 solar masses, like no, even less. 20 solar masses, less than 20 solar masses, but those stars are not super. If they're tiny, they're not super relevant for these kind of processes, because usually they don't inhabit the core, let's say. They are always like expelled out of the core, so the core is really efficiently only populated by the most massive objects, which are either black holes or massive stars. It still could be that maybe, you know, if you kind of are in the region where it's like 5 million years, but you are a bit above, I would say it's reasonable to expect that maybe you have some black holes and some massive stars, but I don't know well what would happen at that point. Probably you would find yourself in kind of an intermediate state in which like you maybe can merge a few black holes with a few stars, but I don't know if there's any prescription for that. But yeah, I mean, at some point we were wondering to like study that. The problem is that you really need to kind of get a grasp of what's going on, and it's a bit difficult. Yes.
Quickly. Thank you very much for this interesting results. So about the Highlander ones, which
Yeah.
I guess it's named because at the end there can only be one, right? So in this case, you have a binary, a binary of massive black holes, right? In the cluster.
You have a binary with a massive black hole, and the other is just a stellar mass black hole.
It can be just stellar mass, because I had this impression that they're both massive.
Okay, so this points out another thing. So the simulations, we have to integrate these simulations with they're called next generations black holes, in the sense that, of course, as the IMBH is growing, also the other stellar mass black holes can grow. And so their mass doesn't follow, let's say, the initial mass distribution anymore, but they can be a bit more massive after some time. And that can have an impact on the IMBH growth. But again, like to this extent, we are only considering first generation stellar mass black holes always. This is not such a bad, let's say, assumption, in the sense that within cluster, what happens is that the growth of a heavy black hole is kind of dictatorial. So once you form a heavy black hole, it kind of like let's say, it doesn't allow the others to grow that much, because of course it's continuously eating up also the other slightly more massive black holes. And so for now, you must imagine that it's always either like a stellar mass binary in our simulations, or it's a IMBH stellar mass black hole. So a Highlander is just heavy and tiny, let's say. I don't know though if you had a question about this. Sorry.
No, I was suspecting that I was having this impression that maybe they're both massive. In that case, or if you have competing massive IMBHs there, because I don't know what is the dynamical friction time scales with respect to the formation time scales of these massive objects. But if you have them competing, then you have a binary that can carve the cluster of, because if you have a binary, you're going to start recoiling the stars that's going to let them to continue. So you have both a topping of the mass of the cluster, because you just lose the stars, and of course stopping the massive. But if it's, as you say, that they're very
it's a bit
high mass ratio, then this effect is minimized.
Yeah, I think this can happen if you have a merger between two clusters, maybe hosting two IMBHs, then that can actually happen. But yes, within the same cluster, it's not so likely to have especially very massive IMBHs coexisting. So yeah.
Thank you very much.
No worries.
Okay. Questions from the audience online?
See a comment maybe here, but
There's
okay.
very beginning. So I assume not. So very quick.
Go ahead.
My quick question is, your simulations start immediately from some program cluster, or do you have set some initial connection line, for example, what with the initial mass function that cluster before you have something?
Sorry, I am not sure I got the question. So can you?
No, my question is, there's any constraint on initial addition of this program cluster, like for example, if I have a different kind of initial mass distribution of mass function, like all to the growth of clusters, it's not one that you much more higher massive stars in the young cluster, or
no, I think that we don't have like a different prescription for the IMF of the stars depending on the cluster. One thing that I want to kind of see though is that of course the less massive the cluster, then less likely it is that you. So in this one quick thing that I can say about this is that wait, no, what was it? So as you see here, the very massive star mass depends also on the seed mass, so which is the initial mass of the star, which is growing. And usually this is expected to be the most massive stars that you have in the cluster, in the sense that the one that has the highest cross-section is the one that undergoes these runaway collisions. But of course, the most massive star that you find in the cluster depends also on the mass of the cluster. And this is not something that we are taking into account now, but there are again like prescriptions to kind of, cut these initial mass for very low mass clusters, and kind of want to see what happens there, but most probably it's going to have an impact only on the very light IMBHs rather than the very massive ones.
You know, start from something like this big life, right?
Yes. So
Yeah, but this is only for certain distribution, right?
yes, I'm not sure I get this.
Here, you has been about the distribution of the stars initially in the cluster, so
Massive.
at least it cannot be anything, right? At least it has to be realized, so we can have a revolution.
Okay. But you're talking about the mass of the stars, I guess, no? I don't know.
I think we are talking about the initial conditions for the simulation, right?
So the positions of the stars and the velocities. I thought you were talking about I was talking about the masses. So
Maybe we can check this detail
Maybe
later.
we move to
Before pizza gets cold, let's thank Lavinia again. Here in the patio.
that's great.